Hi everyone, Assalamualaikum. Today we are going to be talking about standard distribution, the central limit theorem, as well as estimations. So this is the first video for our statistical inference series. Okay, so why do we sample? Well, simple. We sample because we can't obtain the entire population's data. It may be too expensive, it's gonna take too long, or it's just not feasible for us to collect the data for the entire population. Therefore, we resort to sampling. So what do we do with this sample actually? Okay, so with the sample, researchers often study the characteristics of the sample itself. But on top of that, we also make inference about the larger population. But how do we do this? Okay, for you to be able to do an inference about the larger population from a sample, you have to have collected the data using only a probability sampling. Okay, this is only made possible with probability sampling. Right. So if you have all the data in the population, you can calculate the population's parameters, okay, such as the population's mean scores. But when you collect the data only from a sample, then you can calculate the sample statistics. All right. In order for us to understand inferential statistics, we have to understand what sampling distribution is. Let's take a look at the population of my donut here. Okay, so this is just a simple example. You can see that there's 3 donuts over there, the orange one, the pink one, and also the chocolate one. And you can see the price on top of each donut. The orange one is going to be priced at $1, the pink one is $2, and the chocolate one is $3. If I ask you to calculate the mean, would you be able to do so? Definitely, because 1 plus 2 plus 3 is 6, right? Divided by 3, you're going to get a mean of 2. So if you take a sample with replacement, you're going to get the probability distribution. I'm going to show you an example. So every time you take a sample, you can see that the mean for that sample statistics is not going to be the same, right? And it's not necessarily going to be the same with the population mean. So for in this example here, we only sampled the chocolate donut as well as the orange donut, and it's going to give you a mean score of 2, right? Which is equivalent to the population's mean score. But if you accidentally randomly sample the chocolate and the pink donut, it's not going to give you the exact mean score. Okay, so remember we have the orange donut, which is priced at $1, and the pink donut that is priced at $2, and the chocolate donut is priced at $3, right? So the probability of us doing a sample with replacement is going to be orange and orange, and orange and the pink donut, orange and the chocolate donut, and then we have the pink and pink donut, and then the pink and orange donut, and the pink and chocolate donut. Again, the chocolate and chocolate. We also have the chocolate and pink and the chocolate and orange. As you can see, there's 9 different samples there. Okay, so we know orange is $1, $1.02, $1.03. And then the pink is, sorry, how much? Okay, yeah, it's $2 and $2, $2 and $1. This one is $2 and $3, right? So this is 3 and 3. This is 3 and 2 and 3 and 1. Okay, and then you have to calculate the sum. The sum, okay. So 1 and 1 is 2, and then 3, and then you have 4 here, 4, and then 3, 5, 6, 5, and 4. And then you calculate the mean. Okay, so what's the mean for this one? It's going to be 1, right? So 3, 1.5. So this is going to be 2. This is going to be 2. And this is going to be 1.5. This is going to be 2.5. This is 3. Another 2.5. And another 2. All right. So how do we calculate the sampling distribution? Okay, let me just bring this here. Okay, let me draw a chart here. Okay, let's take a look at the mean scores. We have a mean of 1, and then we have 1.5. We also have 2. We have 2.5 and 3. That's it. Okay, so if you calculate, so how many mean scores? How many of the scores are 1? You can see that that's only 1 over 9, right? So there's 1 over 9 chance that when you sample, you're going to get a mean of 1. Alright? Why 9? Where do you get 9? Because the total number of samples that we get here is 9. So what about 1.5? You can see, okay, so there's 2. Okay, so it's 2 over 9. And what about 2? 1, 2, 3. So that's 3 over 9. Sorry, yeah, that's 3 over 9. And then 2.5 is 1 and 2. Again, another 2. Let me change the color here. Okay, and what about for 3? We have 1. If you see, there's a normal distribution there, if you can see, right? There's a bell curve over there. So this is very important because after this, we're going to talk about the central limit theorem, and you can relate to this standard distribution over here, right? Okay, so what is a sample limit theorem? Sample limit theorem is a theory that says if all samples of a particular size are selected from any population, then the sampling distribution of the sample mean is going to be approaching an approximately normal distribution. This approximation improves with larger samples. Okay, to simply put it, if a population has a thick tail or is skewed, 30 or more samples will enable us to observe the normality feature. Alright? So this is what we call a sample limit theorem, and this enables us to do estimations. So basically there's 3 main ways for us to learn about the population parameter from the sample statistics. Okay, so the techniques are estimation and hypothesis testing, and of course under estimation we have point estimate and also interval estimate, or also known as confidence interval, and also our hypothesis testing, which is going to be in another set of slides. Alright, so what is point estimate? So it is a statistics that's computed from sample information, and we use it to estimate the population's parameter. So it assumes population parameter equals to the sample statistics. This is very risky, but this is how you do it. For example, Sanheng wanted to estimate the mean age of people who purchased Sony PS4, the PlayStation 4. They select a sample of 75 recent purchases and determine the age of each buyer and compute the mean age of the buyers in the sample. And they assume that this mean age of the buyers from the sample itself is equivalent to the population's mean. So what about the other one, the confidence interval? Instead of having just a single point, or from the sample statistics, just like the population estimation, in confidence interval, we estimate a range based on the samples, okay? So a range of values constructed from the sample data so that the population parameter is likely to occur within that range at a specified probability, okay? This specified probability is what we call as level of confidence. So 95% level of confidence with 5% error. So this is what the level of confidence, right? Remember all your statistics, p-value must be less than 0.05. So that is from the level of confidence of 95%. So you have to remember about standard deviation, because standard deviation is used to compute the limits of the confidence interval, okay? The result of the central limit theorem earlier allows us to make generalized confidence interval statements using z-statistics when we have the population mean, or using t-statistics when we do not know the population mean. Okay, so here's an example. So this number right here, typically we use the z-statistics, okay, the standard distribution table. Okay, so for example, this is at 95% confidence level, 95% of the data, we are 95% confident that the data is going to fall between this line here, between this range, you see? And this is going to be the critical point. Here, CV is a critical point. This is the point of 1.96. Where do we get this 1.96? That's the calculation there. If you would want to know about that further, I would provide you with a link. Okay, that's from basic statistics. So 95% of the area under a normal curve lies roughly within 1.96 standard deviations of the mean. Okay, and due to the central limit theorem, this number is therefore used in the construction of approximate 95% confidence interval. This is Why does it have anything to do with the central limit theorem? Is because we assume that when your sample size is larger than 30, right, it's still going to be approaching the normality. But sometimes some students ask questions like, if everything is assumed to be normal, why do we still need to test for normality? Because if you simply base on assumptions, like if you simply base on assumptions that your data is normal, fine, go ahead. But a good practice is for you to check normality. Okay, you need to check the normality because not all data is going to be is going to look or is going to be distributed normally. Okay, you can read this on your own because this is just like a threshold for you to be able to understand whether when there's a zero, what does it mean? When there's without zero, what does it mean? Okay, we will learn more about this in our one sample statistics later on. Okay, so this is how you calculate. This is an example of how you calculate interval estimates. For example, a researcher wants to study the blood pressure levels among lecturers in FPHP. He randomly selects 36 lecturers and recorded their BP. The mean BP was 120 with a standard deviation of 5. So you know the standard deviation, you know the mean. He wants to construct a 95% confidence interval for the BP level of all the lecturers at the faculty. Okay, so this is the formula over here. Okay, the formula is estimate plus error. So how do we calculate standard error? This is how we calculate standard error. So mean score plus minus the confidence interval multiplied by the standard error. So do we have the confidence interval? So we assume at 95% confidence level, the confidence interval is going to be 1.96, right? So 1.96 multiplied by the standard error. How do you calculate standard error? It's just this one here, the formula here. All right. Sample, if I'm not mistaken, it's a standard deviation over square root of sample. So that's going to be 120, your mean score, plus minus 1.63. Okay, so when you minus, it's going to be the lower bound. When you plus it, or when you add it, it's going to be the upper bound. So this is what it means. We are 95% confident that the mean BP for all FPHP lecturers will fall between 118 and 121.6 with a margin of error of 1.63 or 1.63 over 120 multiplied by 100. That's going to be 1.36 of the estimate. 1.36% of the estimate. That's all for our standard deviation, central limit theorem, and estimations. We are going to talk about which statistics that you will be using for your research project. Thank you.